Hello, everyone. We are the Protein Evolution Group. For our project, we traveled back in time to the first signs of life on Earth to answer a question for the future. Scientists estimate that life originated on Earth approximately 3.5 billion years ago. Over this time period, life has been able to find different ways to adapt to ever-changing environments and to use renewable resources in a sustainable manner. For example, molecular oxygen was available in the Earth's biosphere 0.5 billion years before it became widespread and was toxic to pre-existing organisms. Now it is considered to be one of the most important molecules governing many metabolic actions in complex organisms. The key for the evolutionary success of aerobic life was the ability to exploit oxygen in controlled reactions. This was made possible by the evolution of enzymes, which are complex protein molecules that act as accelerators to drive biochemical reactions in the body. In terms of oxygen evolution, we are specifically interested in the series of enzymes called oxidases, which catalyze the transfer of electrons from substrates directly to molecular oxygen, harnessing and incorporating it directly into organic substrates.
NICA2, the enzyme which we are analyzing, was discovered in Pseudomonas putida S16 by analyzing genes whose protein products were increased during growth on nicotine. Pseudomonas putida S16 is a bacterium that degrades nicotine, and NICA2 is a flavin-dependent nicotine oxidizing enzyme. Through an experiment, scientists found that NICA2 reduces both nicotine levels and withdrawal symptoms in rats. However, the major obstacle preventing us from using NICA2 as a treatment is the absurdly high dosage required to have an effect because of its poor efficiency as an enzyme. To address this, we applied an ancient process of oxygen evolution to this modern issue. As an electron acceptor, oxygen is a powerful tool for dramatically increasing the efficiency of enzymes. Our goal is to evolve NICA2 into an oxidase to enhance its oxidase activity. This is possible since NICA2 is related to many molecules that react rapidly with O2. Simply put, our essential question is, how do enzymes adapt to use oxygen?
20 years ago, it would be unimaginable to process and analyze as much data as we currently do every single day, and almost all the credit goes to the rapid development of computers and scientific software. Having received more than 40 different sequences from our collaborators, we were able to analyze each of those mutations. The first step was to create a viewable model of those mutations. Swiss model allowed us to create a highly accurate model of each mutation for further analysis, based on the template of the original enzyme. After that, we utilized PyMol, a computational software based on Python, to comparatively analyze the mutations that occurred.
Furthermore, we decided to use the Kava Analyst software and the PyMol plugin version of Kava to be able to calculate and visualize the tunnels, paths of diffusion that the oxygen molecules would take, and allowed us to track the route of molecular oxygen. The results we obtained focused in the vicinity of the active site of the enzyme, stretching all the way to the boundaries of the enzyme, and how the mutations may significantly affect the tunnels leading to and from the active site, thus finding an explanation for increased oxygen activity as we compared the bottleneck radius, the length of the tunnels, the width of the tunnels.
The first part of our project work entailed remodeling the active site and studying how it alters the catalytic activity. For that, we received amino acid sequences of the mutants and afterwards created their visualizations. Using these, we characterized different properties of their active sites, namely the surface area accessible to the solvent of the corresponding residues, total molecular weight, atom count, and total charge. We observed that mutants with higher catalytic activity possess a lower surface area and neutral charge, a higher atomic number, and a higher mass, as one can see on these generated correlation graphs. This indicates that a decrease in size of the cavity containing the active site better sequesters the oxygen molecule and favors oxidoreduction. The reduction in size can be attributed to the bulkier side chains of the residues surrounding the oxygen.
We discovered that out of the 6 residues within 5 angstroms of oxygen, 2 were mutated in high-activity mutants, and 1 was mutated in a medium-activity mutant, resulting in some of the conformational changes shown in Figure 10. These active site results align closely with prior literature, in particular an enzyme theory known as the shifting specificity model. When the cavities around the active site were larger and filled with bulkier side chains, mutants tended to show low activity. But smaller, heavier spaces around the active site were better able to sequester oxygen and stabilized an intermediary known as the transition state. This helped the mutants achieve high binding energy with molecular oxygen and, as a result, high activity. We also found that negative charge is associated with low activity, probably due to incompatible electrostatics between negative residues and nonpolar oxygen.
We also suspected that the mutations have changed the path of oxygen. We then inspected the tunnels leading from the outer surface to the active site with the program CAVA. We first compared the distal entry site in NIC-A2 and MET254, a mutant with high activity. To our surprise, a mutation of residue 130 greatly widened the entry, making oxygen easier to get into the tunnel from the solvent. Next, we compared the proximal entry site of NIC-A2 and MET254. Tryptophan, containing a large flat aromatic ring, blocks the entry in NIC-A2, but in MET254, a nearby mutation in residue 107 moves the ring upwards, opening the entry, just like the sliding door of a Lamborghini. Hence, the tunnel is shorter and more direct in MET254.
These two mutations at residues 107 and 130 are common among the high-activity mutants. Knowing their importance, we noticed that many mutants with lower activity also contain them, so there must be other mechanisms in mutant 254 at play in maintaining the high activity. Compared to the mutant 244, we noticed that their secondary tunnels are different despite sharing the same shortest tunnel. The tryptophan ring in mutant 254 remains parallel, and the secondary tunnel is located right behind the gate. In 244, however, it is twisted backwards, creating a bottleneck and forcing the secondary tunnel to squeeze through the front. This is caused by another mutation at residue 130, changing the local conformation. Therefore, we believe that mutated residues 107 and 130 enhance the activity, while other mutations may destabilize or reverse their positive effects.
To conclude and summarize, we began by looking at the main two possibilities for change in activity, and while the active site gave us telling information about the oxygen activity, we found that the formations in the molecules around the telling site led to much greater changes in oxygen activity. We would pursue more research in how to utilize that. Lastly, we would like to thank and acknowledge our mentor, Jagoda Jablonska, for teaching us, for guiding us, and for giving up countless hours to ensure that this project was completed. And lastly, but not least, we would like to thank the Dan Taufik Laboratory for hosting us. And thank you all for listening.